Beyond the veil of night lies an infinite ocean of stars. Welcome to Cosmic Rings, where the universe comes alive.
In ancient times, tribes of humans would huddle around the flickering light of a solitary campfire, wondering about what might lurk out in the darkness. And in that respect, things haven't changed. Our campfires might be larger now, our vision reaching across the globe and even further, out to the very edges of the observable universe thanks to telescopes like the James Webb. And yet, there is always an edge where darkness falls and it's left to our imaginations to fill what lies beyond it. The observable universe's edge is an impenetrable barrier. It is the section of space that is accelerating away from us so quickly, nothing, not even light, can approach us from beyond that line. And so, nothing beyond it can interact with us causally. So, unlike the darkness that came before, whatever lay on the other side of this particular edge seemed destined to remain a mystery because it could never reach us, and we could never reach it. Or so we thought. But in 2008, hundreds of galaxy clusters were analysed to be drifting towards a section of that edge, faster than science could account for, almost like something beyond that point was pulling them, or had once pulled them, with a reach that extends across billions of light years. Something massive lurking beyond that final dark. This drift of galaxy clusters that spans across the universe has a name: dark flow. What do we know about it? What could be causing it? And what are its ramifications on cosmology? Today, let's dive into the mystery of dark flow and its model-breaking implications for our theories concerning the origin of the universe. Dark flow is a controversial topic, so we'll start with what we know for sure. In 2001, the Wilkinson Microwave Anisotropy Probe was launched by NASA to map out the cosmic microwave background radiation, the fizzling echoes of the Big Bang itself that quietly radiate across all of space, to help us understand better the features of our universe. This map was completed in 2010, although it released its data in installments before that point, and was hugely influential on cosmology as it helped scientists to answer questions like how flat was the universe, or how much of the universe is made up of physical matter compared to dark matter or dark energy. Alexander Kashlinsky was one scientist eager to get his hands on this data. Leading a team of researchers at the NASA Goddard Space Flight Center, Alexander was excited to try to compare the cosmic background radiation map with the motion of galaxy clusters to see if there were any interesting patterns in the flow being witnessed. It was a difficult task. To tackle it, Kashlinsky and his team were taking advantage of something called the kinematic Sunyaev-Zeldovich effect, which was very tiny. This technique essentially makes use of the fact that when cosmic background radiation passes through a high-energy galaxy cluster, it gains a little of that energy. This works whether the galaxy cluster is very hot, thus heating up the cooler cosmic radiation, or whether the galaxy cluster is moving quickly and thus has a lot of kinetic energy to impart. Either way, the radiation gets a little boost, and you can use this information to infer things about the existence or motion of galaxy clusters. The problem is, this boost is so tiny, it's necessary to use multiple galaxy clusters and some statistical calculations to notice it at all. The researchers needed a detailed enough map of the CMB to then be able to compare 1,000 known galaxy clusters against to try to find movement. And to their surprise, they found a pattern. A massive bulk flow of galaxy clusters in comparison to the CMB, stretching 2.5 billion light years away from us across the universe, with clusters moving between 600 to 1,000 kilometers per second in the direction of the constellations Centaurus and Hydra. The mystery is, there is nothing out there to account for this motion. Some massive source, or sources, of gravity presumably had to be pulling these galaxies towards them, but it was outside of our vision, which led to the implication that a particularly large source of mass likely had to exist at or beyond the edge of our universe, just out of sight. And this is a very controversial idea. But first, is it even possible for something beyond the edge of the universe to influence us gravitationally? You might think the answer would be no. As I said in the beginning of this video, nothing that exists out there can now affect us causally, and we can't affect anything out there. That's just what happens when space expands between 2 points so quickly that the expansion outpaces the speed of light. You lose the ability to interact, even gravitationally. I talk about this in more detail in my video on the end of the universe. But there is a loophole if you do that interacting before a period of time in the Big Bang known as the cosmic inflation. For those of you unfamiliar with this concept, essentially, scientists back in the 1970s were wondering why most parts of the universe looked very flat and very much the same in terms of temperature and distribution of mass if you zoomed out enough, even parts that never interacted with each other before. For instance, the edge of our universe to our left and the edge to our right are very similar to each other, even when there was no reason this should necessarily be so, as they've never met. This idea is known as the horizon problem. An American physicist known as Alan Guth realized that the problems raised by this mystery all went away if at the start of the universe everything did interact with each other, evening out like a mixture of blue and red dye in water when shaken around enough. But for that to be the case, and for everything in the universe to then explode out to where it is now, a period of really fast expansion of space was needed somewhere at the start, in addition to the already fast Big Bang itself. It's a little uncertain, but physicists have placed this super expansion as taking place just after the Big Bang began, and lasting only 10 to the power minus 33 seconds, which is not very long. But in that time, it would have expanded by a factor of 10 to the power 26 times, which is insane. This mind-bogglingly fast expansion is akin to going from the size of a bacterium to the size of the Milky Way galaxy, all in a billionth of a trillionth of a trillionth of a second. The nice thing added by having this cosmic expansion event as part of the Big Bang model is that it allows you to explain how everything had a chance to mingle before in the time of the early universe, even the parts that are now unreachable to each other. There are even some very respected theories about how it came about, involving terms like scalar fields and false vacuum state, but that's a little heavy on the physics side and isn't really needed for this video. But the takeaway is this: dark flow could be explained. In that pre-inflationary period where matter wasn't even coalesced into atoms yet, there was a particularly dense section of the wider universe that our particular patch of observable universe got tugged towards on account of it having so much gravity. Cosmic inflation could then have happened, pulling the powerful mass far away from our observable universe to the point where we are no longer gravitationally affected by it. But because things in motion tend to remain in motion, the galaxy clusters given that initial pull are now simply drifting along in that same direction, going with the cosmic flow. But as I said, this is controversial for two main reasons. Firstly, dark flow needs a particularly large amount of mass to exist just outside our universe for it to work and make sense. There have to be far more stars out there, concentrated far more densely than our models currently predict. which flies in the face of the whole reason Alan Guth came up with the cosmic inflation in the first place: uniformity. The universe as we see it is uniform. It is roughly homogeneous, which means that mass is distributed fairly evenly no matter where you look. It is also isotropic, meaning that if you add up all the velocities of everything moving in the universe, it all cancels out. Dark flow upsets this whole idea. It suggests that just beyond the visible horizon, things suddenly stop being so uniform. That dense amount of mass is still in existence, we just can't see it. And that's an idea that's a little out there. It's an idea that raises a whole lot of questions. If the universe is not actually uniform beyond our horizon, did we just get cosmically lucky to find ourselves in an exceptionally flat bit? What does that mean for our theories about the formation of the universe itself and cosmic inflation, if the reason inflation exists is to explain a homogenized universe that isn't actually that homogeneous? The second reason that dark flow is so controversial, though, is that it might not exist at all. Kashlinski's NASA team might be convinced of it, but ESA's Planck team double-checked the existence of dark flow using an even more detailed CMB map, one provided by their own, more advanced Planck probe, which launched in 2009, 8 years after WMAP. After looking through 1,000 galaxy clusters, the Planck team claimed to see no signs of dark flow at all. But Kashlinski and his team then took a look at the Planck data, and they claim that they do see signs of dark flow. So there's still a lot of debate on the issue. Kashlinski and his team announced in a paper that they would be doing an even more in-depth analysis using Planck and WMAP data, intending to establish more conclusive proof, but this has yet to be released. Until we have better proof or indications of this, it makes sense to assume dark flow isn't a thing, and there is no boogeyman lurking just beyond the edge of the light that billions of years ago dragged thousands of proto-galaxies towards it. But as with all unknowns, it does make you wonder. Science does not really care about what's the most convenient answer. Truth is the truth, whether complicated or simple. Perhaps one day we'll somehow find the answer once and for all to what lies beyond the visible universe and whether dark flow is real. But then, all that will happen is the darkness will simply retreat a little further and the next cosmic boundary will appear, causing us to wonder once more. There is always more to know, and humanity's hunger for knowledge and discovery will never cease.